Hi everyone, this is Jayendra Reddy, CSC Data Science student at IIRE College, Hyderabad. Today I'm going to let you know about sum and product of eigenvalues. Eigenvalues. Let X be an eigenvector of the matrix A. Then there must be exist an eigenvalue lambda such that Ax equals to lambda x, or equivalently Ax minus lambda x equal to 0, or A minus lambda I into x equal to 0. If we define a new matrix B equal to A minus lambda I, then Bx equal to 0. If B has an inverse, then x equal to B inverse 0 equal to 0. But an eigenvector cannot be 0. Thus it follows that x will be an eigenvector of A if and only if B does not have an inverse or equivalently det of B equal to 0, or det of A minus lambda I equal to 0. This is called the characteristic equation of A. It's to determine the eigenvalues of A. Now, properties of eigenvalues. The sum of the eigenvalues of a matrix is the sum of the elements of the principal diagonal. The product of the eigenvalues of a matrix A is equal to its determinant. If lambda is an eigenvalue of matrix A, then 1 by lambda is the eigenvalue of A inverse. If lambda is an eigenvalue of an orthogonal matrix, then 1 by lambda is also its eigenvalue. Now, coming to the trace of a matrix. The trace of an n by n matrix A is defined to be the sum of the elements on the main diagonal of A. Trace A equal to sigma I into AII, where AII is the entry on the ith row and the ith column of A. Properties of trace of a matrix. Trace of A plus B equal to trace of A plus trace of B. Trace of C into A equals to C into trace of A. Trace of AB equal to trace of BA. Trace of ABC equal to trace of CAB, that is invariant under cyclic permutations. Trace of A equal to trace of A transpose. Det of transpose trace A equal to trace of det A. Differentiation of trace. Trace of A equal to rank of A when A is idempotent, that is A equal to A square. Determinant of a matrix. The determinant is a number associated with any squared matrix. If A is an n by n matrix, the determinant is det A or det of A. Determinants are used to characterize invertible matrices. A matrix is invertible, non-singular, if and only if it has a non-zero determinant. That is, if det A is not equal to 0, A is invertible. Determinants are used to describe the solution to a system of linear equations with Cramer's rule. Can be found using factorials, pivots, and cofactors. More on this later. Lots of interpretations. Use it for inversion. Example, inverse of 2 by 2 matrix. A equals to A, B, C, D. Then data equals to AD minus BC. Now A inverse equals to 1 adjoint A by data. That is 1 by AD minus BC into D minus B minus A minus C A. This matrix is called the adjugate of A or adjoint of A. That is A inverse equals to adjoint A by det A. Determinant of matrix. Now consider 3 by 3 matrix of ABC, DEF, GHI. Now multiplying the matrix AEI. Now by multiplying the whole matrix we get that of the matrix AEI plus BFG plus CDH minus AFH minus BDI minus CEG. So this is the data of matrix of 3 by 3 row and column. Now Sarah's rule, sum from left to right, then subtract from right to left. Consider three matrices of same values ABC, DF, GHI. The multiplying the B, H and CGI, HBG. Again once more, GBG. Sum of the GBG and HCH and IBG. Then again subtracting from right to left. GBI, ICG, HBG.